Hello, and welcome to my short film on the basic interactions between the atmosphere and ocean. Solar insolation can be described as the amount of the sun's energy that reaches the Earth's surface. There are a variety of factors affecting the amount of solar energy received by the Earth, such as the angle of the sunlight hitting the surface, the distance between the sun and Earth, and the type of surface the sunlight hits. Roughly half of the energy received from the sun is absorbed by land masses and oceans. 30% is then reflected by the surface, atmosphere and clouds, and the remaining 20% is absorbed by the atmosphere and clouds. Because the Earth is spherical, tilted on its axis, and has an elliptical orbit around the Sun, the energy is not evenly distributed across the whole of the planet, and the intensity of insolation varies with latitude and seasons. The equatorial regions receive the most energy, followed by the tropics, and eventually the higher latitudes and polar regions receiving the least energy due to these factors. Heat absorbed around the equatorial regions heats the surface of the Earth. This heat then radiates into the atmosphere. As the air temperature increases, it becomes less dense and rises higher into the atmosphere, where it then cools and sinks again. This process creates a difference in air pressure. The air moves from an area of high pressure to an area of low pressure. We know this movement of air commonly as wind. If the Earth were not rotating, there would be two atmospheric cells created, moving from the equator out toward the two poles. However, the planet is rotating on its axis, making this rather more complicated. The Earth's spin creates a deflection of these air movements. The counterclockwise spin of the Earth causes a deflection to the right in the northern hemisphere and to the left in the southern hemisphere. This is known as the Coriolis effect. The Coriolis effect has a much stronger influence at higher latitudes than at the equator due to the difference in speed of the rotation at the different latitudes. The differences in air pressure and the Coriolis effect combined create three atmospheric cells north and south of the equator. These are known as Hadley cells, Ferrel cells, and polar cells. These atmospheric cells create our northeast and southeast trade winds and our westerly wind systems. The wind is the mechanism which translates the energy from the sun to the surface of the oceans. Put simply, as the winds blow across the ocean surface, the friction generated produces small surface waves, increasing the surface area caught by the wind, and so increasing the friction and size of the wave. Of course, it is not quite as simple as this in reality. When we consider the Coriolis effect, we will see that over a period of time, the surface current will be deflected, just as the air was, to the right in the northern hemisphere and to the left in the southern hemisphere. As the wind pushes the surface water in one direction, the Coriolis force pushes the surface water to the right. The result of these two forces acting together is a movement of surface water at 45 degrees to the right of the wind direction. The movement of the surface layer acts on the layer below it, and so does the Coriolis effect. In each layer, some energy is lost, and the angle of deflection slightly increases. This continues down through multiple layers of water, creating a downward spiral known as the Ekman spiral. Once the spiral reaches a certain depth, the effects of wind and Coriolis act in direct opposition at 180 degrees of each other, and an Ekman current is created, flowing at 90 degrees to the right of the wind direction, depicted by the broad arrow in this slide. When combined, the shallow Ekman currents and the global wind patterns create the five major ocean gyres. The opposing winds direct the Ekman currents into the centers of the ocean basins, creating a hill-like pile of water. Eventually, the water in the center is forced downward below the Ekman layer, where they spread laterally and are again affected by Coriolis force, causing a clockwise gyre generally known as a geostrophic current. As well as the surface currents, there is a second mechanism driving the large-scale movements of the oceans. This is called thermohaline circulation. Thermohaline comes from two Greek words for heat and salt. Thermohaline circulation is part of the large-scale ocean circulation driven by global density gradients caused by surface temperature and freshwater fluxes. It begins at the poles, where surface waters are cooled, increasing their density. Once cooled enough, these surface waters sink, forming deep and bottom waters. The deep and bottom water slowly spreads towards the equator. North Atlantic deep water, combined with bottom and deep waters from the Antarctic, spread throughout the oceans, eventually upwelling to the surface again, where they are driven by surface currents back to their formation sites. This whole circulation process is known as the Great Ocean Conveyor Belt. As was briefly touched on earlier in this film, small waves are created by wind acting on the surface waters. Here we will take a look at waves in more detail. Waves are the result of a disturbing force and a restoring force acting in opposition. Small surface waves created by wind energy are called capillary waves. Capillary waves are classified as having a wavelength of less than 1.73 centimeters. At this point, the restoring force is the surface tension of water. Once a capillary wave grows beyond 1.73 centimeters, the surface tension is broken. The restoring force changes to gravity, and the wave becomes a surface gravity wave. As the crest of a surface gravity wave falls, its momentum causes it to land in a new position. As the wind acts on these waves, they continue to move away from their point of origin. Contrary to what you may picture, it is the flow of energy moving through the water we observe, not the actual movement of water. The water itself actually moves in a near-perfect circle known as a wave orbit. These orbits are not just confined to the surface layer, but propagate down through the water column, getting smaller with depth. There are shallow, intermediate, and deep water gravity waves, and they are classified based upon the depth of water relative to the size of the wavelength. A deep water gravity wave is one where the water depth is greater than half of the wavelength. In this instance, the bottom does not interfere with the wave orbits. As the wave approaches shallow water, it becomes an intermediate gravity wave. Here, the orbits are disturbed and the speed of the wave is effective. When the depth is less than 1/20th the wavelength, the wave becomes a shallow gravity wave. The height of a gravity wave builds more quickly than its wavelength. As a result, a surface gravity wave will eventually collapse or break. This critical steepness occurs when the height reaches 7 times the wavelength, and the breaking wave is known as a whitecap. At this point, the energy input from wind and energy dissipated from the whitecaps is at equilibrium. As deep water gravity waves approach the coastline, the water depth decreases, causing it to transition to an intermediate and then shallow water gravity wave. As the wave is slowed, the waves following behind catch up, building height. Once the depth is around 1.3 times the height of the wave, it will break. These breaking waves are known as surf. The tides could be described as the largest waves on the planet, as they ebb and flow in the same way a small wave does. They are the result of gravitational force caused by the Moon and Sun. As the Earth, Moon and Sun move around relative to each other, altering gravitational forces pull on the oceans, causing our tidal variations, or as we more commonly know them, high, low, spring, and neap tides. Around the globe there are lunar, or semi-diurnal tides occurring twice in a day, and solar, or diurnal tides occurring once in a day. As the names suggest, lunar tides are more heavily influenced by the Moon, whereas solar tides are more heavily influenced by the Sun. There are also mixed tides, where the Sun and Moon both have a significant effect. As well as the gravitational pull on the ocean, there is a centrifugal force created by the rotation of the Earth. This acts on the opposite side of the planet to the gravity of the Moon, creating two tidal bulges. This can be explained in more detail and further using equilibrium tidal theory and dynamic tidal theory. The equilibrium model is based on an ocean planet with no land masses and a uniform ocean where all the water would be pulled in lateral lines towards the Moon. The dynamic theory takes into account land masses and ocean bottom friction and shows how the bulges are actually tidal or rotary waves altered by Coriolis force and the ocean basins.